go ahead and get the recording going. And oh, we got another person.
Hello.
Hello. Welcome. We are going to be talking about the first law of thermodynamics and different thermodynamic processes, if I can pronounce thermodynamic correctly today.
It is a big word.
It's a big word. It's like, what, 5 or 6 syllables? 5 syllables. It's a lot going on.
Syllables.
Yeah. So are you also pointing out that I don't know how to pronounce syllables?
Syllables?
Yes.
All right, get out. All right, so let's go ahead.
Hey, I have a disability about that kind of crap, so I can't.
All right, let's go ahead and start talking about thermodynamic processes first of all. So, what exactly are the 4 main types of processes that we'll be seeing in this class? We have isobaric, isothermal, isochoric, and adiabatic. Let's go ahead and start with an isobaric process. What exactly is that?
The pressure of the system remains constant.
Mm-hmm. So it's a thermodynamic process where the pressure remains constant. And what happens with our other main variables? For example, in our ideal gas law,
Volume changes.
the volume will change, and so if the volume increases, what else changes?
Work. And
Temperature. Yep. Does the temperature increase or decrease with the volume?
it increases?
Yep, exactly. So essentially, with our isobaric process, let me go ahead and sort of write this down. So a constant P, and then if, for example, our volume goes up, our temperature goes up, and vice versa. So what about an isothermal process?
The thermal... Both pressure and volume changes.
And so what remains constant?
The temperature.
Temperature, exactly. So temperature is constant. And so how do pressure and volume change?
They change simultaneously. Like if pressure increases, the volume will also. Oh wait. Oh, if the pressure increases, the volume will decrease.
Exactly. Yeah. They're going to have to change as, so that they're essentially remain constant because the temperature is constant. So what does that end up looking like on a graph, for example? Or if we were to plot, for example, up here, if we plot with our constant pressure, our volume versus our temperature, what is that going to look like at constant pressure? Is it going to be like a straight line increasing?
It's a straight line along... So like the y-axis would remain constant.
So
it would just be a straight line to the right. Yeah.
No, I mean, like, okay, yeah, so you're thinking about a PV diagram. I'm thinking
right.
more about volume and temperature. But yeah,
Oh.
you're right. We're going to get to the PV diagrams later.
Right. So, well, if volume is increasing, or
Mhm.
rather, if temperature increases when the volume increases, then it's just going to be a regular sloped line, an increasing.
So excuse me, a linear slope line like this?
Yep.
Exactly. So we'll say volume, temperature. And what about here? So we said if temperature is constant, we have, if pressure goes up, volume has to go down. And so what is that going to look like on a PV diagram, just because these are 2 variables?
A curve.
What sort of a curve?
Hyperbola?
Not quite a hyperbola. Welcome, Michelle. We're talking about our 4 different processes and what our processes sort of look like in terms of what variables are changing.
Can't remember the name of the curve.
Oh, so what sort of a function does it look like? Like, for example, this would be, for example, just a function of x. Like x to the power of 1. What would it look like down here?
X to the power 2, like an x squared.
X squared, something like that?
Oh,
Yeah.
like a 1 over x.
1 over x, exactly. That's what I'm looking for.
Oh.
So it's going to look something like this.
Actually, yeah, that makes sense. Yes.
Something
Right.
generally that looks like that. It's a 1 over x relation. And so our third process here, we have an isochoric process. What exactly does that mean?
Isochoric, the volume remains the same.
Yep, exactly.
Volume constant.
Sorry, can you repeat that?
That should definitely be the constant of volume.
Yep. And so how do pressure and temperature change with one another at constant volume? So like if pressure goes up, what happens to the temperature?
Should,
I think it should go up.
And why is that, Michelle?
Cause the pressure, cause if you do like if you multiply like with constant volume and then like you have a higher pressure, you'd get like a higher temperature, whereas if you had a lower pressure multiplied by the constant volume, you get a lower temperature.
You're talking about multiplying. What formula are you using?
PV equals nRT.
Exactly. PV equals nRT, ideal gas law. Let's actually go ahead and just we'll put it in the little text box at the top. PV equals nRT, and then there's another way we can write this formula. How else can we write this? Instead of nRT, what can we use?
Yeah, crap. Where'd I put that formula sheet?
Does he give it to you on the formula sheet? Yes, he does.
yeah.
Yeah, he does. I do remember seeing it.
Is it the big NK?
Yep, exactly. Big N KBT. So, what's the difference between these two N's?
There it is. Yeah.
One's for the molar and one's for the number of molecules.
Exactly. Which one is which?
Big N is number of molecules.
Exactly. Big N is the number of molecules. Little n is the number of moles. So essentially just big N divided by 6.02 times 10 to the negative times 10 to the 23. So, and then our two constants, R is our gas constant, whatever, 8.3, whatever. It's in the formula sheet. And then K, Boltzmann's constant, it's like what? 1.38 times 10 to the minus 23. So what do we said we're talking about our ideal gas law, and so what would our relation between pressure and temperature look like on this graph? Would it be a linear increase once again, similar to volume and temperature, or is it going to look more like our pressure and volume relation?
It should be like a vertical line. Okay.
You're thinking about a PV diagram?
Okay.
I'm just talking about the relation between pressure and temperature.
It would be the same as the first diagram.
Exactly. Just a linear increase where obviously they meet at 0, and it's just a linear increase from there. Now, we have one last process. We have an adiabatic process. What exactly is an adiabatic process?
It's when there's no heat change. So heat doesn't flow in or out of a system.
Exactly. There's no change in heat. What the hell does that mean? So, like, we can have energy flowing in and out of a system in an adiabatic process, but none of it is heat. So,
Our internal energy equals the negative work, basically.
exactly. And so, what law did you use to get that?
Delta U equals Q minus W.
And what is the name of that law?
First law.
First law of thermodynamics, which you guys will learn to love and cherish and use for the next week, and then you'll forget it all because you never have to look at this thermo stuff for the rest of the semester. It's wonderful.
So, boo, I guess?
I mean, it's honestly, it's really convenient if you are not a STEM major, or like not a, I guess more specifically, especially chem majors and biochem and chemical engineering, where they like actually use a lot of thermodynamic stuff. They take this class, they get their thermodynamic stuff at the beginning of the class. Oh, sweet. And they spend the entire rest of the time messing around with electric fields and magnets, and they don't even have to worry about the stuff on the final. They forget about it. Then they get to their 300 level thermo classes. They're like, oh crap. But for the comp sci majors in this class, and for the mechies that don't have to worry as much about thermo, they still do a little bit. They're like, oh, sweet. We don't have to worry about this stuff. Get it over with in the first 2 weeks, or in this class, 1 week. So you mentioned the first law is what, that delta U is equal to Q minus the work?
Yeah.
Mm-hmm. Q minus work. Also, welcome, whoever just joined. We're talking about the first law of thermodynamics now. What exactly is this work? Is this work being done on the gas?
By the gas, I believe.
Yeah, exactly. It's work done by the gas. So essentially, it's work going out of the system. So, how exactly does the first law change with each of these four processes? We have a constant pressure process, constant temperature, constant volume, and a no heat flow. One is really simple, right? And you guys actually already mentioned it. For an adiabatic process, what happens?
Oh, the internal energy is just equal to the work, or negative work.
Exactly. The total change in internal energy is equal to just the work that's done by the gas. Really simple, because Q is 0, you just ignore it. Now, what about these other processes up here? So let's start with, randomly, with no reason, no rhyme or reason, we're going to start with the constant temperature process. How does our first law change in a constant temperature process?
The change of temperature equals the change of U, the delta U.
Pretty much.
Which is 0.
Yeah, exactly. I mean, so how is delta U related to temperature specifically?
It's directly proportional to each other.
Mm-hmm. And what's the formula?
Is it K? Well, like the formula for what exactly?
For delta U, relating delta U to the temperature, or the change in temperature, actually.
I think it's it's like directly proportional to the translational kinetic energy.
Mm-hmm. And what is that?
I think it was like 3. Was it 3 halves kBT or something.
Mm-hmm. Yep.
Okay.
So it's more specifically, that would be for a single molecule with 3 degrees of freedom. Essentially a monatomic molecule. So the more general way we think about it is delta U divided by the degrees of freedom. All you need to know for this is if it's a single molecule, that degrees of freedom is 3. If it's 2 molecules, it's 5. And anything more than that, you don't cover in this class, and you don't ever have to worry about it. And I never actually even covered it in my 300 level physics class, so W. So it's delta U over degrees of freedom is equal to, you mentioned it was kBT, right?
Mm-hmm.
And there's one more thing if we want to talk about the, not just one molecule, but an entire, system of molecules, like a whole gas.
Isn't there a half in there?
Oh yeah, there is 1/2. And then there's one other thing we need to know, or we need to account for.
Is it just N?
Exactly, N, the total number of molecules. And we also, I forgot a delta T right there. But so our delta U divided by the degrees of freedom, which is usually going to be 3, sometimes 5, is equal to 1/2 N kBT. In this case, it's 0. So that means that Q is equal to the work done by the gas. Pretty simple, right? Anyone have any questions so far? All right. In that case, let's go ahead and cover the last two. Let's do our constant pressure example. So how is our first law of thermodynamics affected in a constant pressure example? How specifically, how does it change?
You'll have both heat and work, but the work is just going to be the area under the curve.
Well, the work is always the area under the curve, right?
Right.
So how is that simplified with a constant pressure example?
Sorry, what was the question again for the work? Yeah, it's just the pressure times the change in volume.
Exactly. So it's just the pressure times the change in volume. I'm just gonna do this is equal to P delta V. Right? So what is the more general example? So welcome. We're talking about first law of thermodynamics and how it's affected during each of our 4 processes.
Oh, okay. Cool.
Yep. So what is the more general example when we don't have constant pressure? How do we get the area under a curve?
Oh, integrate.
Integrate, exactly. What's our integral?
The integral from the initial volume to the final volume, and then
pressure, and then the change of volume, right?
Exactly. PdV. Boom. That's all we're asking for here. So we know that when the pressure is constant, our integral gets simplified to just a pressure times the change in volume. And that will, it makes it simpler for us to talk about the actual values in a thermodynamic process. Now, our last example, we have our volume is constant. So, since V equals 0, I'm just going to write these here. So, how is our first law affected by constant volume?
You said first law?
Yep.
If there's a constant volume, then we would have to. Well, we can't integrate then, right? Or we can't use that integration. for the PDV since the volume is constant?
Well, sure, we could integrate. What are we going to get if we integrate?
Work should be 0.
0.
Yeah. Oh, okay. Yeah, that's what I meant.
Yeah.
Yeah.
I mean, you had the right idea. You just weren't quite getting that. You were 95% of the way there. But yeah.
Yeah, pretty much.
We can't integrate because it's a vertical line on a PV diagram. So the area under the curve is 0. So delta U is just equal to Q. Boom. Everything we just covered is everything you need to know to solve every single problem you will see in thermodynamics in this class. Which is wonderful for the next 3 days, and then you never have to worry about it ever again. But literally, all you need to do is break it down step by step. If you know the first law of thermodynamics, and you know the ideal gas law, PV equals nRT, or NKBT, you can solve... Oh, go away. You can solve every single problem you will see on your quizzes the next 2 days.
I hate that. Go too far down and that pops up.
Yeah, oh boy. I'm going to cover here. Oh, cool. There's an air quality alert. Interesting. Good thing I'm not
already out there doing all that stuff. So
Yeah, I was going to say, good thing I'm not going outside today. So, that's basically it. Anyone have any questions about this?
So, I guess that the work done by the gas equals 0 only in an isochoric process?
Yep.
Okay.
The total work done by the gas is 0 just for when the volume isn't changing. So obviously, if the volume's changing, you can sort of think of it as imagine a balloon. As the balloon expands, the volume increases, it pushes out on anything outside of it. So that would be
right.
Work done by the balloon.
Okay, that
And
makes
then
sense.
as it deflates, work is being done onto the balloon, so it's negative work done by the balloon. So essentially the air outside of it compresses it inward.
Got it. Okay.
All right. Well, in that case, if there's no questions, let's go ahead and hop into our example, where we're going to actually go ahead and cover all 4 of these in one sort of 4-step cycle and just see what happens. So we're going to go ahead and go and box this area off here and zoom back in. So we're going to have an ideal gas, monatomic ideal gas, to make things simple. It's going to undergo a 4-step cycle. First, it's going to isobarically expand, then it's going to adiabatically expand, then isothermally compress, and then isochorically return to its initial state. So first thing we want to know is, what is that going to look like on a PV diagram? And second, how is the internal energy going to change in each step? Is work being done on or by the gas in each step? And then for the whole cycle, is net work going to flow in or out of the gas? So first of all, let's take 10 minutes, and then we'll talk through it together. And if you have any questions, feel free to unmute your mics and ask. Go ahead.
Okay. So I guess this pertains to the recording. So this is uploaded to Blackboard.
I am uploading them to YouTube, and I'm posting the links here on Discord in the session videos text channel.
Okay.
It's right above the voice channel.
Okay.
Unfortunately, my internet is sort of doo-doo, and I'm uploading this plus my 121 session that happens. I host the 121 session right after this, and I upload them both tonight before I go to bed. On Tuesday it took 6 hours to upload both of them. My download speed's wonderful. I can stream everything in 1440p with no issues, but then my upload speed is like, yeah. I mean, I'm probably gonna upgrade my internet when I move out, because I don't need as much download speed, but my dad's paying right now, so and all
So,
he
yeah.
does is stream Netflix, and that's all he needs it for.
Okay, thank you.
Yep. All right. So, let's go through and break down our 4-step cycle step by step and try to understand what exactly is going on. So, first of all, we want to draw these on a PV diagram, right? You guys have been seeing some cycles and some different processes drawn on PV diagrams. What do each of our 4 processes look like on PV diagrams?
So we know what is it? Isochoric is a straight line going up a horizontal or vertical straight line.
Yep, exactly. Vertical straight line.
Isoboric is the straight line from to the right.
Iso what?
Left and boric.
Isobaric. Yep. Isobaric is just a straight horizontal line. And what about our other 2 processes?
Isothermal is a curve.
Mm-hmm. And what kind of curve?
Would it be the 1/x curve?
Yep, exactly. It's that same like 1/x curve that we saw earlier. Now, what about our adiabatic process? What is that going to look like on a PV diagram?
It's a steeper curve than the isothermal.
Yep, exactly. It's going to be a curve that is going to fall faster than isothermal. You know, something like this. And
okay.
we can just be hand wavy with it because reality is that's all you need to understand for this class is isothermal 1/x curve, adiabatic. It's also a curve and it falls faster. But we can just leave it at that, or we can also sort of try to understand why it does that. Does anyone know why it does that? Or can anyone sort of tie it together using your formula sheet?
So let me pull up the formula sheet. So when we're looking at the isothermal equation for is it work we're looking at, or
Well, let's see if you can figure it out.
go
Say what you're gonna say. I want to see
so
if you
what
get that.
what I was going to say was, since their equations are similar, but the difference is that isothermal, the constant temperature that you have, like now the variable is going to be the change of volume, while in adiabatic you're looking at the constant, that's your moles, and then that CV mole, so the change of temperature. So I feel like the one variable of the change in temperature is going to be greater than the change in volume, which causes for that steeper decline.
Okay. I can see how that makes sense. I'm gonna keep it $1.50. That went straight over my head, though.
Yeah,
And it might have gone over some other people's heads. But but you understand that, right? It makes sense to you. Perfect.
Yeah.
So, anyone else want to give their sort of own explanation? All right. Then I shall bestow my knowledge upon, or the way I understand why it falls faster. So the way I think of it is, for an isothermal process, we have PV initial, we have our initial pressures here, are equal to, our initial pressure times our initial volume is equal to our final pressure times final volume. aka PV is equal to a constant, right? PV is equal to some constant, we'll call it C. So then if we plot them with volume as our dependent variable and P as our independent, P is equal to our constant over V. It's our 1 over X curve from before. Now with an adiabatic process, we have this PV to this constant gamma. So PV to the gamma is equal to a constant, so then it's PV to the gamma, if I can draw a gamma tracing with my mouse, is equal to C. So then P is equal to C over V to the gamma. Now, what's the value of gamma? Does anyone know what it is?
The value of gamma is that that specific, what was it, specific heat for pressure or volume, depending. So I'm looking at the equation sheet and it has CP mole slash the CV mole.
Mhm.
So that was like the 14 point something or the 20 point something.
So
rate.
which one is greater, CP or CV?
CV.
You're saying CV is greater?
No, sorry, CP. CP is greater.
Mm-hmm. It also gives you this on the formula sheet up here,
Yeah.
where for a monatomic ideal gas, CV for a mole is going to be 3 halves R, and for CP it's going to be 5 halves. Essentially, our gamma for a monatomic gas is 5 over 3, and for a diatomic gas it would be 7 over 5. So essentially we have C over V to the power of something greater than 1. So that means it would end up falling faster because the denominator is larger. That's the way I think about it. Does that make sense to everyone?
Yeah.
Okay. So now let's go ahead and actually graph these. So our first step is our isobaric expansion. That should be pretty simple, right? It's just going to be some sort of a horizontal straight line, something like that. Next, we're going to have our adiabatic expansion. It's going to be an adiabatic process, and the volume is increasing, so it's going to be going down to the right, something like that. Our next step is an isothermal compression, and our isothermal process is going to be on some sort of a line like this, either going to the right or to the left. Does anyone know what these lines are called along which an isothermal process occurs? You have like multiple of these lines all sort of parallel-ish to one another, as parallel as you can be with a curved line.
I know it's supposed to be like representing low temp, mid temp, high temp. I just can't remember the actual. Did I put that on you? Okay, I know what you're talking about. I did not put the name on there.
Well, I'll give it to you. It's called an isotherm. Isothermal process occurs on an isotherm. But I'm giving to you because you understand it. What's special about each individual isotherm? What occurs along an isotherm? What thermodynamic variable is special along an isotherm?
The temperature?
Exactly. What about it?
It shows that it's either a high temp, mid temp, or low temp.
So along one individual isotherm, does the temperature increase or decrease or what?
Along one, I don't think you can tell if it's along one.
Well, if we have an isotherm that looks like this, what's the temperature at this point? We'll call it T1.
Oh,
What's the temperature over here? Is it greater than or less than T1? Or is it just T1?
Is it just T1?
Yeah, exactly.
yeah. It should be just T1 because our isothermals are constant, so that should also mean that the isotherm should be constant.
Yeah. And yeah, what I was looking for is constant temperature.
Okay.
Yep. So we know it's an isothermal process, and it's compressing. The volume's decreasing. So that means we're going to be wanting to go to the left. So it's going to look something like that. And then our last process is an isochoric process where we return to the initial state. Isochoric, constant volume, it's a vertical line. So it's going to look something like that. Boom. That is our pretty basic, crude drawing of our thermodynamic four-step cycle. So let's go ahead and actually also label these. We'll call them 1, question mark, 2, 3, 4. So now we want to know is how does the internal energy change in each step? So let me actually go ahead and make a little graph. So we're going to have delta U, and we'll have our work for P and C. For step 1, how does our internal energy change for step 1? Is it going to be increasing or decreasing?
It should be increasing.
Mm-hmm. And why is that?
Because the change in volume is going to be in the positive.
Mm-hmm.
Yeah, since we're going from a positive direction, it should be the change of volume will be positive, so that means the change of initial energy should be positive.
But the internal energy isn't a function of volume, is it? What's a function of? What is it a function of?
Wouldn't that be? Oh, I was thinking about work there. Whoops. Put that one in the wrong spot. But oh, whoops, temperature. I looked away. I looked away. And
Yep.
I just looked. And I was like, oh.
Yeah, it's a function of temperature, and temperature increases with volume if our pressure is held constant. So
Yes.
essentially, we know it's going to increase, and it's going to be a function of 3/2, and then we're going to have N, K, delta T. And if we solve for delta T using the ideal gas law, what do we get? What is our ideal gas law again?
PV nRT, right? PV equals nRT.
Yep, and then we
And
get
if you solve for it, you'll get PV divided by nR.
and little nr is equivalent to big NK, so it ends
Yeah.
up canceling out here. So we get 3/2 P
PV
delta V.
or delta V, yeah.
Yep, that's how our internal energy changes. And so, and what would our work be in this example? We'll move along from each process to each process. How do we get our work for an isobaric process?
It's just P delta V.
Yep, exactly. It's just P delta V. So then, from these, we could then just use the first law of thermodynamics to actually find the heat flow as well. So let's go ahead to our second step. Step 2, an adiabatic expansion. Is our internal energy going to increase or decrease here?
Decrease.
Grease.
Decrease, and why is that?
Because the slope is decreasing.
The slope is decreasing. Okay. So what does that mean about the temperature?
Oh, that means the temperature is decreasing.
Mm-hmm. Exactly. We are essentially, remember how we like drew those isotherms?
Yeah.
And each isotherm, let me actually sort of like draw them in red. We have these different isotherms here. We're going down from one isotherm to another and whatnot. Essentially, we're going down and we're decreasing in temperature, which means our internal energy has to be changing. So do we know how to solve for it?
Well, adiabatic, it says that delta U is just the negative work done
Exactly.
by the gas.
Exactly. It's the negative work. And how would we get the work?
N, well, small n, and then the CV mole, and then change the temperature.
Yep. So we have N, CV, delta T. And that's something we got from our formula sheet. And if we wanted, we could actually mess around with the first law to actually derive that. But it doesn't really matter. And you guys can worry about it if you ever take a 300 level thermo class. Or you can just not. And that's totally fine. So now for step 3.
Somehow shows up on the quiz.
Somehow shows up. No. You guys won't be expected to derive that. It's a 100 level physics class. So step 3, we have our isothermal compression. What is our internal energy going to do in this case? It's going to increase or decrease?
Increase.
Why is that?
Because because pressure is increasing.
Pressure is increasing, but volume's decreasing, right?
Right. But what we learn is that as a gas is compressed, that applies more work to the surroundings, right? Well, it's okay. Well, that no.
You're overcomplicating it, and
Yeah.
also you're wrong.
Yeah.
Anyone else?
Delta U should equal delta T, the change in temperature.
Which is
0.
0. There is no change in internal energy because the temperature does not change. So you're right, the pressure increases, but the volume also decreases to equally and perfectly balance that out. So now, how do we get the work?
Find Q.
But what's Q?
0.
No, Q's not 0.
Q is not 0. Q is
Q was 0 in the last process.
Yeah. But this one, it's nRT and then ln change of V.
Yep, exactly. It's nRT. Then we have our natural log of ln of the ratio V final to V initial. Does anyone know how we would derive that?
Derive that?
From the integral, right?
Exactly, from the integral.
Well, yeah, from the interval.
If you don't get an A in this class, I'm going to be extremely disappointed. You knew that right away. I'm going to be real. You noticed that it comes from the integral. You noticed that right away. I'm going to be real surprised if you don't get an A in the class. Yeah, it's just the integral of 1 over x is the natural log.
Yeah.
That's some real physics major intuition. So now,
or heck calculus rolls that into his head, one or the other.
yeah.
Seriously, some of the derivatives you have to do in calculus. Oh God.
Yep.
It's a pain. It's just sticks in your head though.
Yeah. Has anybody
Yeah.
done calculus yet, which is multivariable calculus?
Thank God, no. I skipped it. I
Oh.
just went straight to stat.
I took it my sophomore year. I never went to lecture. I had a Galbraith or whatever.
Mm-hmm.
He's basically reads from the textbook in lectures, so it's pretty boring. But
Yeah.
I
I had an A for mine. Thank God. It was really good.
yeah. I somehow got a 99 in the class though, so I'm not really complaining. All right, so our last process, we have our isochoric process where we're returning to the initial state. What happens to the internal energy in this example? Is it going to increase or decrease?
It will equal Q, and that should. That should increase, I believe.
Mm-hmm. And why is that?
Oh, because pressure is increasing?
Exactly. And so what increases because of the pressure?
Yeah. That's
The
part of it. Temperature increases too.
Temperature increases. Exactly. So there's actually a way we can write this that's not in terms of just... Because the formula sheet just says, oh, it's just equal to Q.
Yeah.
There's a better way we can do that. How can we do it?
Wouldn't that be the ideal gas law?
Mm-hmm. And how...
That would be T final over T. When I'm looking at the equation sheet, that'd be T final over pressure final is equal to T initial over pressure initial.
So how do we use that to relate to delta U?
Let's see. We could use the initial or the full equation of PV equals nRT, and then eliminate what was it, nR from the delta U, and then we'd be left with what was it, E, and the change of T, and then we could work with that.
Applause! Applause! There we go. That's the more physics major intuition. But yeah, we literally, you take our ideal gas law, and then we substitute it into our first law. Or sorry, not our first law, our delta U equation, similar to what we did up here. So remember, it's 3/2. Let me write that better. We have 3/2 NK, then we have delta T, which we know is because our volume is constant. We have PV, so delta T is just essentially V delta P. And then also we have the NK, which ends up canceling out. So we have V delta P. It's the same, sort of like the same process we did up here. And so then what would the work be?
None.
Zero.
Zero. Exactly. No area under the curve. Zero work. Does that make sense? Anyone have any questions?
That makes sense.
Yeah.
All right. Now, one last thing. What would the total net work being done by the gas in this cycle be? Would it be positive or negative? Would work be flowing out or would work be flowing in?
Let's see. The first part is positive, so So since work is positive on the first part, that should be going into, correct?
Mm, not
I'm
quite.
just trying. I'm trying to.
It's the other way around.
Oh, it's the other way around. All right,
Yep.
so it's positive.
It's
It's
like,
going out.
think of it this way: the volume is expanding. It's pushing outward. The balloon is
Okay.
pushing outward on the air around it.
Okay, so the first two, it's definitely moving out since they're both expanding.
Exactly. Work is
And
coming
since
out.
since temperature is compressing, work should be going in.
Yep, exactly. For this one, work would be going in.
So we got, and then fourth part
We said it was 0.
is 0, so that doesn't.
So
it's work going in.
you're,
Yeah.
you're saying the total net work is going in?
No, sorry, it's going out because the area under the curve is work, correct?
Exactly. And
Yeah.
And the area under the curve of both of the process of 1 and 2 is greater than the area under
exactly,
the curve of
it's
3.
all this area here versus going back, it's just the area down here.
Yeah. Okay. Okay.
So our total work out, that's a U. The work is going out in total. Does that make sense?
Yeah,
Yep.
it does.
All right. Anyone have any last questions before we go ahead and wrap up the session?
So the quiz is tomorrow,
Last I checked.
okay, and it is going to be on what this SI pass was
For the most part.
for the most parts. Same amount of questions. What was it? 7?
Yeah, your quizzes are going to be sort of similarly structured to what you had yesterday.
Okay.
Well, I think it's going to be 6, since that one question was literally us saying we will not cheat during the quiz.
Oh yeah, that point one.
Yeah. But
6.
it's
literally was it. So
some
I'm getting 6 questions.
some of the quizzes are a bit shorter, like there'll be less questions, but they'll take you more time, obviously. And
Okay.
other
Question
quizzes,
1. Hay part.
yeah. But yeah, they're generally pretty reasonable. Like if you 100% knew what you were doing, like someone like me who is experienced with the material, I could bang through the quiz in about 10 minutes. And for you guys, it'll take you a bit longer, obviously, but you have a whole half hour, so you guys will be fine. And remember, all you need to know is first law of thermodynamics, our delta U is equal to Q minus work, and the ideal gas law, or little PV equals nRT up at the top. Those two equations is all you need to know for your quiz tomorrow.
Which 2?
The first law of thermodynamics and the ideal gas law. That's literally the only 2 equations. If you were like trying to minimize the amount of material you were memorizing for the quiz, that's all you'd need. From those 2, you could theoretically derive everything else you cover in the quiz.
Right.
But I also recommend taking a look at... Is there a way I could get rid of this? There we go. Beautiful. But I also recommend take a look at this table. It really helps out with understanding things and also gives you some freebie equations that you don't have to derive that are sort of a bit annoying and ugly to do. And just get comfortable with PV diagrams, and that's it. If there's no more final questions, that's it for today. Thanks everyone for coming. Hope this helped out. Hope you had some fun. And same time on Sunday, covering tomorrow's material to prep for Monday's quiz.
All right.
That's it.
Great. Thank you.
Have a good day, everyone.
You too.
Thanks for coming.